Hey everybody, this is Alex Merced, host of gnarlydatawaves, and for another exciting week of exciting data knowledge. And this week we'll be talking about optimizing your data files in your Apache Iceberg tables. So different performance strategies such as sorting, compaction, ZOrder, all sorts of really good stuff. But before we do that, again, your weekly reminder that the Dremio Datalakehouse platform is easy, open, and fast. Okay, and basically that means it's going to give you that data warehouse-like functionality and performance with that data lake flexibility all in one nice, easy to use package. Now, you could just take my word for it, and I promise you, I'm telling you the truth, but nothing's going to help you better than actually getting your hands on and seeing it firsthand by heading over to dremio.com and clicking that test drive button. So that way, within a few minutes, you can get hands on with the Dremio platform, see what it has to offer, and see it for yourself. Okay, so go try that out over there at dremio.com. Again, that's called Test Drive. And yeah, I promise you'll like what you see. Okay, and again, we got so many great episodes coming up of Gnarly Datawaves, so make sure you keep tuning in every week. Subscribe on Spotify, iTunes, where make sure you don't miss an episode. But this week we're talking about optimizing data in Apache Iceberg with compaction, sorting, zeroing techniques. Next week is Apache Iceberg office hours. So you bring your Apache Iceberg questions, we'll bring our answers. How to modernize the data lake house with Dremio and Apache Iceberg. So how to move Hive tables over to Apache Iceberg. Top 5 considerations for migrating Hadoop to cloud data lake houses. So again, a discussion about just sort of like why would you want to migrate from Hadoop to the cloud data lake and what that journey would look like. So make sure you don't miss any of these fun, exciting topics. I'll see you all there. But with no further ado, we're going to get into today's feature presentation, which is optimizing data files in Apache Iceberg performance strategies with my colleague Dipankar Mazumdar, fellow developer advocate here at Dremio. Dipankar, the stage is yours.
Hey, Alex, thank you so much for the introduction. Hi, everyone. My name is Dipankar, and today we are going to talk about something called optimizing data and files in Apache Iceberg, which is pretty important for all the performance strategies in your data lake or data lake house. So yeah, I'll just dive a little bit into me. Currently, I'm a developer advocate here at Dremio, and I focus on a couple of open source projects such as Apache Iceberg, Apache Arrow, Project Nessie, and also the product itself within the Dremio Lakehouse platform. In the past, I've been involved with like BI and machine learning and data architecture, so that's kind of my background. I'm also going to take this opportunity to introduce everyone to our new upcoming book, which I'm also co-authoring with other folks within our team. It's called Apache Iceberg, The Definitive Guide. And this book really is the first Iceberg book that we have, and we're hoping to have this release later this year. But the first chapter is out for everyone to go and read about it, and we will incrementally adding the more chapters as we write more chapters. So this is a good way to even get feedback that you have from the community as well. So yeah, please reach out to me if you have any questions, if you need to get a link to the book. I also have put up a QR link, as you can see in this particular photo of the book. You can just scan the QR and basically read the first chapter of the book. Okay. So in terms of the agenda, I will first introduce you to the Apache Iceberg table format. I won't deep dive more into the format. This is more of a session where we will dive into more of the performance strategies and stuff. And then we will go through some of the problem, right? With the ever-increasing data in our data lakes, we have more data coming in. So we'll go through those problems. And then we will finally discuss a few solutions and how Iceberg, being the table format, brings all these advantages natively, right? So we can have faster user-facing queries. And finally, we will end with discussing some of the advanced techniques to deal with organizing the data files in our data lake. Okay, so that's pretty much the concise agenda. So over the years, organizations have been investing heavily on building centralized, reliable, and scalable data platform, right? So the whole idea was that if they could democratize data, it would allow data consumers such as analysts and scientists to leverage it further and enable analytical workloads such as BI and machine learning and whatever it is on top of it. Right? So data warehouse were kind of the first one that enabled to deal with this, but then it also lacked abilities to deal with unstructured data, right? So for more advanced use cases such as machine learning or streaming, right? There was no way to, intrinsically, naturally, being able to use the data warehouse to do that thing. So then came the era of data lakes with the Hadoop ecosystem, right? And Hadoop, the boom was great, and the data lake file system was also great. Organizations could basically dump all of their data, whether it's structured, unstructured, it didn't matter. You can just put all the data in the data lake. Now, with the rise of cloud and its cheap price over the years, we have now the cloud data lake storage, right? For example, Amazon S3, Azure Blob, Google storage as well. So now we have all this cloud way of storing data, and like that's really a great advantage for organizations and for individuals to like use it for such a cheaper platform, and also at the same time have that control of their particular data, right? The problem with this data lake was that it basically lacked those atomicity and consistency guarantees. You cannot basically do ACID-based transactions on the data lake. So what I mean to say is that you cannot really write something or read something into the data lake from a data lake and without having those guarantees, right? It's really a risky thing to do that. For example, some of the writes that you might do, it might not be a complete write as well. It might be just a partial write. You don't have those guarantees of those consistencies, right? And also it was getting really hard to get a sense of all the data. It was really hard for an analyst or a data scientist to like do all this processing and make sense of all of the data, because it was just in a form that it was such in a raw form, right? You cannot like really make sense of it. So this gave rise to a new form of architectural platform called Lakehouse, which is basically, if I have to put it like in a simpler term, it's the best of the data warehouse world plus the data lake. So now you can basically run any workload that you could do in a data warehouse and also take advantage of a data lake, which is really great. And we have the best of the both of the worlds, like I said. Now, the most important thing that makes up a data lakehouse is the table format. Okay, that's what we're going to focus on right now. So more generically, if I have to talk about more of a simpler term, what a table format does, it basically organizes and manages all of the raw data files into a form of a table, right? And we have historically seen with databases and everything how it's easier for query engines to query the data when it's in the form of a table, right? Everything is in a structure. And our discussion today is about this particular table format called Apache Iceberg and its performance strategies. Okay. Now, Iceberg wasn't the only table format. Obviously, for a while, we have had the Hive table format, which was developed by Facebook or Meta, like in the past, and which is really important, right, for us like to lead us to today, right, how we have today Iceberg and other formats. But Hive also had this a lot of performance issues, correctness issues, and it wasn't really great for at-scale analytics. Okay, so that's why that kind of like led us to Iceberg, right? So now these problems were pretty much common in every organization doing large scale analytics, right? But Netflix were kind of the main one to look at this problem, and they were thinking that instead of putting a band-aid on each of this individual problem, can we just take a step back and see the actual issue and see the problem? So one case study that I wanted to share quickly is from Netflix's system called Atlas, which is a time series based metric system. It's just 1 month of data, and as you can see, it's close to 3 million files in that 1 month in 2,688 partitions, right? So the problem with their environment was that they cannot process more than a few days of data. Okay, so if you take a look at this particular query, you want to just find the distinct type within the tags field, and they wanted to look at a single metric, just one single metric, right? And it's just a week range of data, which is a fairly straightforward and simple query, right? You're just looking for a weeks of data and you're just trying to get the data. Now with the Hive table format, this particular query took Netflix 10 minutes to just explain the query, okay, and not even execute the query. So just getting the files and planning the query took the majority of the time. Now with Iceberg, when they replaced the Hive table format with Iceberg, this same query took 42-second overall wall time, okay, and just 25 seconds to plan the query versus the 10 minutes planning time with Hive. So that's a significant improvement, right? That's a huge improvement in terms of query planning and executing the query. So that is kind of what led to the motivation of Iceberg and how we have the robust table format today in today's world of data lakehouses. So to summarize, Iceberg is an open table format for analytical data sets in the data lake. Okay, it brings in capabilities such as ACID compliant SQL queries, ability to evolve schema, do time travel, and all sort of data warehouse related things that you would expect. And architecturally, Iceberg has been divided into 3 main components, all layers, as I would like to say. The first is the catalog layer, which is basically used to maintain all those atomicity guarantees, all those consistency I was talking about. The second thing is the metadata, which is another key component in this kind of a table format, right? You want all this metadata information to keep a track of all the data files and help with performance and everything. Okay. And the third one is the data layer, which is actual data files, which are a Parquet file or org file or Avro file or whatever it is. So one thing that I wanted to take away from this particular presentation is that Iceberg allows multiple engines to work on the same data set at the same time. So it's really important to understand that you're not limited to just one processing engine like Spark. Depending on your workload, you can use various engines or tool, whether it's a, ad hoc SQL kind of thing, whether it's streaming, whether it's machine learning or whatever it is. So that's the benefit with Iceberg. Now, in terms of where Iceberg sits in a lakehouse, if you're new to the environment of like data lakehouse table formats and everything, this is how I would like to like visualize it in my way. So the data lake storage comes in the bottom part where you have the raw data files landing in a cloud data lake storage, such as S3 bucket or something like that, right? And the table format is just a layer on top of that data file. So basically, you're basically using that table format to manage all those data files, okay? And then you have the engines on top of the table format, which is what basically I was talking about, whether it's distributed like SQL, whether it's you're using something like Spark, or you can use something like Dremio for your ad hoc SQL requirements and performant BI queries, and also something like Flink for real-time streaming data. So this is how basically the overall picture of a lakehouse would typically look like. Obviously, the best part about that is that you can mix and match, and you can have different engines and different things coming over in this particular way. But this is one of the way. Okay. So everything is going great, right? Your data is in open format. Your multiple engines can use the data based on the specific use cases, and you don't have to really pay a high cost for a data warehouse, compute, or storage, right? But that's really just the beginning of your journey. You want your lakehouse to be operational and functional, right? So that means you will have various sources ingesting data in your data lake storage, right, over a period of time. And this means that as you go on and as your lakehouse becomes functional, the number of data files in your data lake is also just going to increase by a lot, okay? So what this means is that, let's say you had a query like this, like select star from movies, from Iceberg table, where basically you put some kind of a filter and you're trying to get the data. So now over a period of time, when you have a lot of data coming in this particular data lake, you might not have the same performance as you had before. And it can be pretty slow and frustrating for users, right? So the gist of all of this particular thing is that querying 100 of petabytes of data, which is pretty minimal. And, we have also seen like some of the data lakes having like, exabytes of data, like, for example, Pinterest, they have a lot of data in an environment as well, even for major companies like Apple as well. So querying 100 of petabyte of data demands optimized query speed. You need a really good query speed, right? And your queries are fast today, but they may not be over a period of time. And there can be a lot of reasons because of why. First, your query patterns may change, right? You might have new query patterns that you kind of added to your queries. And also the queries may be slow because you don't have files organized in a way that really gives the best of the performance, okay? So what are some of the main issues, right? If I have to kind of like take a deep dive and understand like, okay, what is really bugging my system, right? What is it that's kind of making my query slow? The problem is that you might have a lot of unorganized file and small file. So that are basically the two kind of like main issues that you see. So do we have a solution to this problem? Like, the way the files are organized or the small file issues, right? Well, the only solution to this whole problem is just to read as less data files as possible. That's the only solution, okay? So in the best case scenario, we basically need to fetch data from the exact set of files we need to answer a particular query with, okay? But obviously that's a tough game, right? With so many files in a large storage system, like, big data system, it's really tough to like, go through and like analyze and, open each and every file and try to figure out the data that really satisfies the query, right? So the idea is to be able to just skip some of the file, right? I mean, if we could just let our query engine skip the non-relevant file, right? That should give us whatever we need for our query, isn't it? Like if we can skip that non-relevant file, we will have the relevant files. And that brings us to what we can do to optimize this and make our queries faster. And this is where Iceberg shines and brings along things such as partitioning, compaction, MetricsBased filtering, and all those things that we are going to discuss today. Okay, so we will start first with partitioning. Partitioning, as we all know, it's a fairly common technique. It's a way to make query faster by basically grouping similar rows together when we are writing the data. So let's say we have a logs table, as we can see in the left-hand side here. It consists of a couple of data files. Obviously, like here, I have represented with Parquet file, but technically it can be anything else. And now if we run a query to get some of the log entries data, including, let's say, a time range field. For example, if you look at this particular query here, we are trying to get the level and the message from the log, basically between this particular 2 dates, time interval, which is 10 to 12 p.m. And we are looking for only the 1st of December 2018 data, right? So in this particular case, to satisfy this particular query, if we don't do partitioning, we will have to look into the entire set of file to see which row exactly matches our predicate, right? But if we apply partitioning in this particular log table and partition by something like date of event time, we will have groups of log event file with the same event date. Okay, so for example, as you can see here on the right hand side, we have partition A for event data 1st December, right? Similarly, partition B for event data 2nd December, and so on, right? So this way we have different partition or group of similar rows of file. Okay, so now instead of looking into the entire table of data files for a query engine can basically skip the data files in partition B and C because they are non-relevant, right? We are only looking for 1st of December. So we can just go and take the data from partition A and get the value from there and satisfy the query. So partitioning basically allows us to do data skipping and helps ensure the performance part, right? And obviously partitioning isn't, like I said, it's not a new concept. Like we have had this with databases, we have had this with other table formats like Hive. But what Iceberg brings to the table is something called hidden partitioning, okay? So Iceberg, basically what it does, it handles the tedious and error-prone task of producing partition values for rows in a table. Okay, so if we go back to the Hive world, what you have to basically do in order to do a partition is you have to explicitly add a partition column, which means user need to know about the physical layout change of the table, right? So for example, I have put out a query over here in this particular slide. As you can see here, in order to insert that particular, in order to have that partition, we need to explicitly add that partition value over the column over here in this particular query. And so the users, when they're querying that particular table, they also need to supply that particular query, and they also need to know about that particular column, which is used to define that particular table, right? However, in Iceberg, you don't really have to do that, okay? Iceberg basically takes care of all of these, and it basically internally tracks the relationship between the partition column and the actual column, okay? So even in the world where you're trying to evolve the partition, right, there can be scenarios where you want to change your partition strategy, right? You will need to take care of rewriting your entire queries if you are in a Hive table format, because obviously, you explicitly added that particular column, and that basically needs to be rewritten when you're changing the strategy. Okay, so Iceberg takes care of all of this. You don't even need to think about like changing your partition strategy. If that's something also, that's pretty much given with Iceberg. So that is pretty much about hidden partitioning and partitioning within Apache Iceberg. Our next optimization method is called compaction. So basically, when you're ingesting data frequently, specifically with streaming data, right, there may not be enough new data to create optimal data file sizes. So normally you would like to read optimal data file sizes, which is like 128 MB or 256 MB. And this might not be possible when you're like writing smaller chunks of data, specifically with streaming use cases, right? So this problem can lead to a lot of small number of files in your data lake. And this is a very common problem in the big data world that we have seen, the small file problem, right? So this particular problem can really impact your performance for a couple of reasons. A, the number of file operation grows, right? For example, you really need to open each and every file. You need to read the content of the file, and you need to close the file as well. So this particular operations, the 3 operation, it only multiplies with the number of files that you have, okay? So it's a really expensive task, right? And next, there are incentives on the read side as well to read larger block of file versus reading smaller ones. Like I said, your reading side incentives are that you can read larger block of file at one go versus reading smaller files. Also, in Iceberg, the more data files that you have, that means you will also have more metadata files stored in the manifest file, okay? And small data files, they can cause unnecessary amount of metadata file, which really needs to be cleared up, right? And that's a problem, right? It can lead to like performance issues as well. So to tackle all of these issues, we need to have a way to compact the small files into larger ones, right? What if we can compact those one into one larger file? And basically, Iceberg provides mechanism out of the box to do so. So if you're using something like Spark as a query engine or a compute engine, you can use the API, which is there is a procedure as well called rewrite data file section, which by default provides a strategy called bin packing for compacting those files. So essentially what it will do is it will read those smaller files and rewrite them into larger files, okay? And this is a less costly operation in terms of the memory, and it's great, right? You are able to have one large, bigger size of file, and that means your processing is going to be faster. So compaction in Iceberg really helps us to deal with the problem of small file. And this is another way to have less number of files in our data lakes. Okay. Our next topic, which is our next optimization strategy, is called metrics-based filtering. And this is an interesting one, okay? So metrics-based filtering is another way to read less file and skip them, okay? So the file formats like Parquet or org, right? They keep certain information or metadata about the inside content of the file in their footer, okay? As you can see in this particular example here, there are 3 columns: employee ID, employee name, and employee salary. And each of these particular columns have a mean and a maximum value, right? So now if my query requests for, let's say, employee ID 56, we know that the record isn't going to be in this particular file because obviously the mean is 1 and the maximum is 40, right? So this is a pretty helpful information for the query engine before even we need to open the file and read it and close it, right? And what Iceberg does is it elevates this thing to the next level. So it creates its own set of metric-based file called manifest to basically eventually skip as much of this Parquet files or this, this kind of file. So now you have kind of a second level of pruning, which is amazing, right? You don't even need to read those Parquet files and you can just skip those Parquet files, which is really great. Like, it helps with all the performance and everything. But even with that, there might be some scenarios where you have overlapping metrics. Like, for example, let's see a scenario here. As you can see, in both of this file, the metrics are pretty much similar, right? File 1 has the employee name column in the range of A to J, and file 2 also has a similar range of A to J, right? Now, let's say you run a particular query called, select star from employee, where employee name equal to Dennis, right? Pretty simple query, right? You're basically using a filter to get the, all the details of the employee. Now, this particular query has this particular predicate or the filter on the employee name field, right? And the value Dennis is between A to J. The problem here is that this particular A to J range exists in both of this file, right? So even though there is this mean max value, the query engine still has to look into both of this file, right? So now that means that the statistics of this file weren't really helpful in this particular case, right? I mean, there was no real benefits of this. So for a situation like this, can we optimize the layout of the data within each file and further help in the data skipping process? That's the question. And a common strategy with Iceberg to address the overlapping metrics kind of scenario that I kind of just presented is that you sort the data within a file based on the metrics. Okay, so sorting is a technique that is used to do that. So sorting the whole data set, it reorders the data in such a way that each data file ends up with a unique range of values for the specified column it is sorted on. So in our case, if you're using something like Spark as a query engine, you can just call the rewrite data file action, which basically we also use for compaction. And here, all you need to do is, like I said, you just call it with that particular API and just provide a sort strategy and whatever sort column you want to sort on. So now if we kind of apply this particular sorting algorithm, we now have the employee name A to D in one of the file, anatometry, and D to J in another of the file 2. So now if you run the query, the previous query, which is select star for employee and where the name is Dennis, the query engine now has to read only one file, right? It basically has to read the first file. So it doesn't even have to go and read the second file. So by changing the layout of the data using a technique like sorting, we were able to answer the query by reading only half the data file, which is really helpful at a larger scale, as you can imagine, right? And well, it's not like you can just sort one column in your table, right? It's not like that. You can also obviously hierarchically sort the column, right? What I mean to say is, like, you can sort first by employee name, followed by employee salary, followed by employee ID, and so on, right? And if you have a query with a filter on all of this field, right? For example, like, consider this particular query, right? Select star from employee, where we have predicate employee name equal to Dennis, employee salary equal to 25,000, and employee ID equal to 22. Now, what the engine will do is it will compare the mean max ranges of each of this column to filter the file, right? So that's good, right? When you want to use sort, when you want to sort using multiple column and you have this filter on all of this particular, sorted column that you have kind of already sorted on. However, there is a problem here as well. And what if a query is something like this? So select star from employee where employee sal is greater than 18,000. Right? So here we don't have the filter on the first sorted column. Our sort order was employee name, employee salary, and then it comes as employee ID, right? However, here what we had is the filter is on the employee salary column, which is not the first sorted order, okay? So in this particular case, the mean max ranges, the statistics of the other column, they may not be beneficial to skip the data file because Well, let's take a hypothetical example just to simplify it. Okay. So consider that the table now has two columns, employee name and employee sal. Okay. The range of the employee name column is Anna to Julian, right? And employee salary is 10 to 20K, right? So now if we sort this particular table in the order, let's say employee name first and then employee salary. Okay. You sort that in this particular order. And now you rewrite this particular file into 4 evenly, size file. Okay. So the files may look something like this. Okay. So the first file contains all the employee name in the A range and employee salary in 10 to 20K. Similarly, the second file has the employee name in the B range and employee sal of 10 to 20K and so on, right? And this is because the engine will first sort the data with employee name, okay, and then scatter the rest of the data for the other column based on that employee name column. And that's why you see the employee name being sorted and, employee salary being still there as a constant, right? So if you run the same query, select star for employee where employee sal is greater than 18,000, which has a filter on the employee salary column instead of the first sorted column, which is employee name in this particular example, you are now back to the same problem, right? Your engine still has to scan all of the 4 files because you don't have a filter. Your filter is still not applied. Like your filter still goes on that particular range. So it still has to scan all those 4 files. So in the case of hierarchical sorting, you will only benefit if you have a filter on the first sorted column. Okay. So the engine cannot take advantage if the filters are on the other fields in that particular hierarchy. Okay. But how do you optimize the query when you have multiple dimensions to filter on? So that's our next question. So I still want to use, like, there are going to be a lot of like queries where you have multiple filter, right, on multiple dimension. And you still want to use to optimize the queries when you have multiple dimensions to filter on, right? So that brings us to something called multidimensional clustering, okay? And an important aspect to basically consider while reorganizing the data, when we're kind of reorganizing the data in each file, is to keep the closely related data point in the same file as they would have been in a higher dimension space. So in more simpler term, if you look at this particular table, it has like a couple of employees, obviously, but let's say we take Anna and John from this particular list, right? So if you project them in a 2-dimensional space, like in the form of like a graph, 2D graph, and based on their value of employee salary and the years of experience, you can see that they're pretty close, to each other, right? They have a similar salary range. They have a similar year of experience as well. So let's say you want to run a query on this particular table. For example, let's say, give me all the employees who are 5 years experience, more than 5 years experience, and have salaries over $10,000. Okay. So this query now would require you to combine both the filter, right? Both the employee salary and the years of experience to narrow down your search query, right? Now, in an ideal world, when you group this particular data files by sorting, you want to have all the employees with similar data points stay together in a similar file. And that's what I was talking about a few minutes back about, keeping closely related data points similarly in the same file. Okay. Why do you need to do that? Because otherwise the query engine has to read data from multiple files, right? Which means it's more IO, and which is kind of ineffective, right? So for queries like this, when you want to be able to preserve the locality of the data points, right? So they stay close even when they're projected to a single dimension. This is where things like ZOrder clustering comes into picture, okay? So we're going to quickly discuss on ZOrder clustering before we end the presentation. But before that, just to recap, we discussed 2 problems until now with metrics-based filtering. One is the overlapping metric scenario, if you can recall, where we had similar min-max ranges, similar statistics for different files. And that kind of led us to a problem where we were not able to really prune the data files based on the statistical values, right? And the second problem was, how do we keep the similar data points together in the same file, like for this particular example as well? How do you keep similar data files together, right? So these problems ultimately boil down to one particular question. Can we use information from multiple columns in a more integrated way? What I mean to say is that, can we use it in a more together way versus independently using it, right? With sorting like we saw. And in this way, can we better cluster the data by multiple fields? Because we want to obviously leverage multiple dimensions and multiple fields. And the good news is that you can do obviously all this with ZOrder clustering, okay? So I won't go in depth with the math in this particular session of ZOrder and how the ZOrder value is calculated. And neither have I much, gone into that level of detail as well. But by definition, it's a type of a space filling curve that tries to keep similar data point together when mapped from a similar higher dimension to a lower dimension. So for example, 2D to 1D or 3D to 2D, right? So what happens is when you apply the ZOrder algorithm, it basically calculates a value called Z value, and then it tries to organize the data based on that Z value similarity. So if two particular instances have similar Z values, they're going to end up in a similar file. That means they're going to be pretty much close together in a single dimensional environment, right? So now, let's say for our example, which is our employee example, now if we organize the file based on the ZOrder curve, you should be able to use information from both the column for clustering the data using the Z value. So let's say, we apply the algorithm of Z-ordering and rewrite the data files in a way that we want to. Our new file may look something like this, okay? For example, in the file one, we have the salary range of 10 to 12K. The years of experience is 5 to 8. Similarly, in file 2, we have employee sal in 8 to 10K and year of experience in 1 to 4. So now, as you can see, we have, even though we use a kind of like a clustering or sorting algorithm, we're still able to use information from both the column to, rewrite the data. So now if you run the same particular query, which is like get all the employees with experience greater than 5 years and salary greater than $10,000, now the engine, what it has to do is it can just fetch the data from one single file, which in this case is file 1, right? It doesn't even have to go and look at the file number 2, which is really great. You are basically at a larger scale when you have a lot of files and you apply this technique, it's going to be really beneficial for your performance benefits. So using ZOrder clustering, you can now be efficient with filter on multiple columns. You have to remember that particular part. Your whole use case of scenario is that you want to use multiple column for filtering. And also you can keep similar data point together. Like we talk about the co-locality part, right? Where we have similar data points together, like the Anna and John, right? And this allows us to have better min-max pruning and IO compression. And now we can skip and efficiently have better performance for our faster queries. So Apache Iceberg provides the ability to organize the layout of the data using ZOrder technique out of the box, right? You don't have to implement this on your own. There is an API already there. And even if you're using something like Spark, there is even a stored procedure tool, like literally just call that procedure and, apply ZOrdering, okay? So the rewrite data file action in Spark is basically what we applied to even do the compaction and the sorting that we kind of did earlier in one of the slides. So it's the same kind of action file. You just need to call that particular procedure, and you need to pass on the particular values, which are like, you need to pass on the table name, as you can see, the strategy type, the sort order, which is ZOrder, and the type and the fields that you're going to apply ZOrder to. Okay, so that's all you need to provide, and you will end up with the files that you would want in a way that you would want to write them in your data lake. So one important thing to note here is that ZOrder can be a really costly operation, right? It's really costly as compared to like compaction or like sorting, right? So you really, as an organization, as a data engineering organization, you should really put some considerations to when to ZOrder versus when not. We are also we also suggest people overall focusing on these strategies to really have a kind of a flow chart where you need to understand a strategy, where you need to have a strategy of where you decide to do compaction, when you need to do things like maintenance of the metadata files and those kind of stuff. So it's really important to have those design consideration, when you're deciding your data engineering strategies, right? But there are a couple of common scenarios when you can use ZOrder versus when not. And obviously this can vary depending on your goals, like I was mentioning. But I have basically listed out a couple of scenarios to when you can ZOrder and when not. First, you can ZOrder for frequently run queries when you want to filter data using multiple dimension. Remember, we talked about the problem, how we kind of saw, right? We were good with even sorting data, right? But then we ended up with not being able to use multiple dimensions, right? The filters, right? It only sorts on the first sort order, right? So that's a problem. So when you're using a lot of queries in your environment, when you have a lot of multiple dimensions in a filter, that's when you can run ZOrder filtering and those kind of things. If most or all of your queries are kind of on a single filter, that's all right. You can just do normal sorting, will work fine here. Next, ZOrder works best with data that have similar distribution and range. That's super important. So for example, we saw in our example as well between Anna and John, right? They were pretty similar, right? So we would want them to be similar even when we put them out in a file, right? So that's super important. And in a realistic world, this can be super important when you have like IoT data, right? When you have like geospatial data. For example, consider the latitude and longitude, right? For example, you're running some queries on a city and they have the same latitude and longitudes. You'd want two cities to be really close to each other based on that similarity, right? So ZOrder keeps similar data files in the same file to efficiently skip data file. And this is not possible with normal or hierarchical sorting. Number 3, Z-ordering on field with the very small distribution range isn't really beneficial as the data points are already close to each other, right? In a very small distribution range, you will have already data files which are very close to each other. So that may not be an ideal scenario where you want to apply Z-ordering. And given that it's a really costly operation, you might have that consideration as well. In such cases, normal sorting would again work best. Also, the fourth one is columns with higher cardinality, which is large number of distinct values. So those are really suited for Z-ordering, versus other technique like partitioning, where you might end up with a lot of small files. Like when you have a lot of high distinct value, when you do technique like partitioning, you will end up with a lot of small files, right? So in this particular case, you may need to apply something like Z-ordering, and overall that should be the plan for applying Z-ordering. So these are a couple of scenarios. Again, these are not like the silver bullet scenario where you have a lot. This is the only way where you can apply Z-ordering. Obviously, we have seen different people using different strategies and all sort of thing. But these are some of the considerations that you might have in your environment. That is pretty much all. Just to summarize, we talked about compaction. We talked about how we can have a lot of small files in our data lake, right? And how we can deal with basically compacting the small file into a larger block of file so that our query engine have that read side advantage and everything, right? And then we have techniques like partitioning, which is hidden partitioning in Iceberg, where you don't need to even think about like adding an explicit column. And user queries are not really dependent on the physical layout of the table. They don't need to look at a physical level. They only need to understand at the logical level. And then you have things like mean max filtering with Parquet files, and like how Iceberg maintains a manifesto file where you have all the statistical information like lower and upper bound of the column, like the null value counts, those kind of stuff you can use to really prune the files, right? And finally, you end up with technique like sorting, where you kind of sort the data. You basically like organize the data in a way that's kind of like in a way that it's best for our query engines to read that particular data file, right? And then for multiple values, obviously you use technique like Z-ordering. So that is pretty much all that I wanted to cover today. And just reach out to me like in case you want to discuss more about this performance strategies in your organization. And we are also working on something that should be pretty cohesive to like just take a flow chart like to understand like when you can apply what. I think that should be a good way as well to understand when to apply these particular techniques. But yeah, I'm happy to take any questions that you might have now. And thank you so much for listening to me. Right, let's take a couple of Q&A. I think I have 2 here as now. So one question that I have is like, is Iceberg format similar to Delta format? Yes, so Delta and Iceberg are kind of the 2 table formats that are available for applying on top of your data lakes. Again, there is something else called Apache Hudi as well, but yeah, these are the kind of in respect to the types. Yes, these are the similar types of data lake table formats that would help you achieve all the things pretty much that we would expect from data warehouse kind of environment. Another question that I have quickly is Iceberg table format a virtual or light layer on top of the actual data files? That is right in a way. Ultimately, what we are doing with Iceberg or any other data lake table format is that we are putting everything in the form of a table so that it's easier for you, like for query engines to query the data or like, apply all sort of optimization strategies and all the techniques that we kind of talked about today. So yes, it is a layer on top of the data lake, on top of the actual data files, the Parquet files, or the org files, or the Avro file, which basically allows you to manage those files. So another question that I have from Matar is, can you please go over hidden partitioning again, comparing to Hive? Yeah, just to quickly recap, Matar, like so in Hive, with Hive environments, you will basically have to explicitly add a column, a partition column when you're trying to add a partition strategy. So the caveat with that is that since you're explicitly adding a column, the users will need to know about the physical layout, right? They would still need to know, because everything in Hive is like directory based, right? So they would still need to know the actual directory, like the path of that to put it into that query request. So it's kind of really hard, to basically maintain those things. And, things like hidden partitioning, what it does is Iceberg doesn't need you to like maintain those kind of explicit column. It keeps basically some kind of a transformation between the column that you want to like have the partition on, so that Iceberg internally tracks that particular reference and understands it that this is the partition that I have to refer to. And things like partition evolution is something very common as well in organizations. So that is something that it's really helpful with. I can also share a blog later, Matar, if that's something that you want to like go deep dive on. Another question that I have from Raja is, does rewrite data file also regenerate manifest? Rewrite data file is this procedure that has a couple of options to do, like, clear up manifest, to, basically, compact this small files. So if a question is around like compacting those smaller manifest file, yeah, for sure, you can do that. But if you want to do other activities, like, for example, like, sorting or something like that, that procedure still has the options and arguments to do that. Another question that I have from Satya is, while running ordering, will there be any slowdown on inserts or updates? So in general, you have to be a bit considerate when applying techniques like ordering. I would say in terms of inserts or updates, there should not be any impact in general. But obviously, like, it should be something that should be specifically focused on during read time. So that is something that you have to consider. I have another question from Henry. It says, data warehouse has transactions so that parallel writes can properly happen. How does Iceberg properly handle this? So Iceberg uses something called optimistic concurrency control, which is basically like, if you have two operations going on, whatever comes first will basically succeed the operation. And if something fails, they will have to retry that operation again, right? So this helps basically everything in Iceberg to be able to like do concurrent writes and those kind of transactions that you'd expect from a data warehouse environment. So Iceberg takes care of that using that kind of property. All right, Matar, I can share that article, and even if something that is regarding Hive to Iceberg, conversion, that is something also I'll be sharing with you after this presentation. So I think that is all as of now. I think if there is nothing else, we can probably end this conversation. Thank you so much for listening to this.